Hi everyone, welcome to General Chemistry 1. The slides presented will roughly follow Chapter 1 in your OpenStax Chemistry book, 2nd edition, which is the textbook we will be using in this class. The first chapter is all about those essential ideas that you need to learn in order to be successful throughout the rest of this course. Topics will include learning about matter, and then developing some classification schemes for matter, as well as different measurements and how to convert between different units. Let's get started. What exactly is chemistry? Chemistry is studying something called matter. We're looking at what are the properties of matter, the composition of it, and what types of transformations can matter undergo. Matter can be described in 3 different ways. We can talk about the macroscopic scale, which would be what we see in everyday life. We can look at the submicroscopic scale, which would be things that are invisible to the eye. And then we can also learn about the representational form of matter. So in chemistry, the representational form is very important. That's where we're looking at different chemical formulas and equations, different symbols. So if we think about an example using water, the macroscopic scale would be that we see water in a glass with our everyday eye. What we're not seeing is what is that molecular structure of water? What are the elements that make it up? So water is H2O, and we can see that it has a very definite shape, the molecule does. The bond angles are about 104.5 degrees. There's a discrete length between an oxygen and a hydrogen atom. And our representational form of water would be simply using the chemical formula H2O. So those are all ways to represent the same thing. Chemistry is a lab science, which means that everything we've learned has been gathered by experimentation in the lab. The scientific method is a process of gathering that information and formulating explanations. The steps are, first we ask a question, something we wish to know about. Then we gather data via observations and experimentation. From the experiments that we've already done and the observations we've seen, we can come up with a hypothesis as to what we think is happening. A hypothesis is a tentative explanation. Following our hypothesis, there's going to be some more experimentation. We want to analyze the results of our experiments and see if they agree or disagree with our hypothesis. From that, we can come up with a conclusion. Conclusions lead to 2 different things that we'll talk about more in depth on the following slides. We can propose what's called a theory, or we could develop a scientific law. We can see that the end goal of the scientific method is to get some results that contribute to a body of knowledge. If the results yield constant observations, that's what's called a law. If the results support your hypothesis, but we're not entirely sure why, that's where they become a theory. So now let's compare and contrast scientific laws with that of scientific theories. A law is something that describes relationships among observable phenomena. They're based on the results of many experiments, and we know that they're always going to be true. When we see a law, we're going to want to associate that with a mathematical equation. So, for example, you may have heard about Boyle's law in a previous chemistry class. Boyle's law says that the pressure and the volume of a gas are inversely proportional to one another. So we can see on the left side here that there is a large volume of gas. And that means that those gas particles are not having as many collisions with one another, and therefore the pressure is going to be lower. On the right-hand side, we can see that if that imaginary piston is moved all the way down, that the pressure of those gas molecules is going to be much higher because now they're crammed into a smaller volume. So Boyle's law you may have seen as P1V1 equals P2V2, and that's something that we'll be talking about at the end of the semester. Some other laws that you may have heard about, such as the law of gravity, law of motion, and there are actually 3 laws of thermodynamics that we'll talk about in this class. So as we saw, laws are represented by mathematical equations. A law tells us what happens, but it doesn't offer any source of explanation. We don't know why the things happen that they do. That's where a theory comes in. A theory is a well-tested explanation of the behavior of nature. Theories are not always 100% correct, and they can be changed over time, so theories can be updated as new information is learned. An example of a theory is something like the Big Bang Theory. We said that chemistry is the study of matter, but what exactly is matter? Matter is anything that has mass and occupies space. So examples of matter is most of the things around you. A book, the desk in front of you, the person sitting next to you, rocks, water, the air around you. It's easier to probably think about what isn't matter. Examples are time, sounds, your memories, gravity, sunlight, and heat. We now know that matter needs to have a mass and occupy a space. But what is the exact difference of mass versus weight, which is our more common unit of measurement? Mass is defined as how much matter there is in an object, whereas weight is the force with which an object is attracted by gravity. So for example, if we compare our weight on Earth versus our weight on the moon, it'll be different. If we have a person who weighs 120 pounds on Earth, they'll only weigh 20 pounds on the moon because there's 1/6 as much gravity on the moon as there is on Earth. But that same person will be 54 kilograms on the Earth and on the moon. So 54 kilograms would be their mass, whereas 120 pounds on Earth or 20 pounds on the moon would be their weight. So weight changes depending upon gravity, whereas your mass would always remain constant. In this class, there are 3 different states of matter that we are going to be studying: solids, liquids, and gases. Solids have a fixed shape and a fixed volume. As you can see, the particles in a solid are very close together with little wiggle room between them, so they have very restricted motion. If we compare that to liquids, they have a fixed volume but no fixed shape, so we know liquids will take the shape of their container. The particles are close together, but not as close as in a solid. They're actually able to flow and move past one another. Lastly, gases have no fixed shape or volume, so they'll expand to fill an entire container. The particles are spaced very far apart and are flying past each other and hitting the walls of the container as well. Next, we're going to look at a scheme for classifying matter. Matter can be described as either being a pure substance. A pure substance is something that has a constant composition throughout, or it could be a mixture of pure substances. Mixtures have variable composition throughout. Pure substances can be broken down into 2 things. They can be compounds or they can be elements. Compounds can be broken back down into their elements through chemical reactions. Elements can be combined with other elements to form new compounds. On the mixture side of things, mixtures can be described as being either homogeneous mixtures. Those have the same properties throughout. They look like they're one phase. Or they can be heterogeneous mixtures, which have 2 or more phases with their own set of properties. Elements are substances that cannot be broken down into simpler materials by chemical reactions. They are the simplest type of pure substance. There are many different types of elements all around us. For example, sulfur is an element. It's made up of only one type of atom, which are sulfur atoms. Gold is an element. It's made up of only one type of atom, which are gold atoms. And carbon is an element. This specific Carbon is diamond, which is an allotrope of carbon. Carbon can be in the form of graphite or diamond. Some elements occur naturally as diatomic elements. That means that hydrogen occurs as H2 in nature, nitrogen N2, oxygen O2, fluorine F2, chlorine Cl2, bromine Br2, and iodine I2. You need to know what these 7 diatomic elements are. An easy way to remember this is to use the acronym BR Inkelhoff. To remember, and then remember that each of them occur as a diatomic element. If you look at the periodic table, you'll see that different 1 or 2 letter symbols are used as abbreviations for the names of the elements. And it's important that we distinguish between these. So for example, when you see a capital H, that represents the element hydrogen. If you see a capital A and a lowercase l, that stands for the element aluminum. Capital F, lowercase e, stands for the element iron. And you might notice that Fe are not in the word iron. That's because they come from the old Latin names ferric and ferrous. It's important that you use the appropriate capital letter and lowercase letter designation. For example, CO is not the same as capital C, capital O. The first one represents the element cobalt, whereas the second one represents the molecule carbon monoxide. So we have to be very careful about distinguishing between the appropriate elements or compounds that we're talking about. Elements were the first type of pure substance that we discussed. The second type of pure substance is called a compound. A compound is formed by 2 or more elements in a fixed proportion by mass. So these are also pure substances, but they're made up of 2 or more elements together. So for example, water, which is made up of 2 hydrogen atoms and 1 oxygen atom, that would be considered a pure substance, and that's also a compound. Sodium chloride, which is the systematic name for table salt, is made up of sodium ions and chloride anions, but it's still made up of 2 different elements, so sodium and chlorine together. And another example of a pure substance would be hydrogen peroxide. Hydrogen peroxide is also a molecule made up of hydrogen and oxygen, but it's attached differently than we see in water on the left. Now, elements can be combined together to form these compounds. That would be a synthesis reaction where you take 2 individual elements and you put them together to make something new. Or we can take these compounds and break them down into the elements that make them up through a decomposition reaction. So we could take something like water and decompose it down into hydrogen, which we know is a diatomic element, and oxygen, which is another diatomic element, through a process called electrolysis, where we input energy to break the molecule down into its respective elements. When we were learning about classifying different substances, we talked about pure substances, which had 1 phase throughout, and on the other side of that, there were mixtures. Now, mixtures have a variable composition. They can be made up of a mixture of compounds with different elements, or you could have elements mixed with other elements, or you could have compounds mixed with compounds. When we look at the types of mixtures that there are homogeneous mixtures, which are also called solutions, or there are heterogeneous mixtures. Homogeneous mixtures are going to be mixtures that look like they only have 1 phase. So for example, if we look at this cup of orange juice and imagine it does not have any pulp contained within it, we could see that there's only 1 phase, but we know it's not just made up of 1 thing. There's water in there, there's sugar in there, there's maybe some ascorbic acid, which is the other name for vitamin C, but it looks like 1 phase. Black coffee, we can imagine that there's caffeine in there, there's water in there, There's all kinds of tannins in there that give it the nice dark color, but it still looks like one phase throughout. Air is a mixture of different types of gases, such as nitrogen and oxygen, and it all looks like one phase. We cannot see any distinct phases throughout the air. Now, some examples of heterogeneous mixtures where there's two or more phases. If you look at something like Italian dressing, which contains oil, water, vinegar, seasoning, we know that oil and water do not mix. They're immiscible. And so it creates a phase. Chicken noodle soup. This is another example of a heterogeneous mixture. There's distinct phases and pieces and parts that we can see throughout. So you're looking for those multiple phases that are distinct in a heterogeneous mixture. All right, let's go through and do a learning check. Classify each of the following as an element, compound, homogeneous mixture, or a heterogeneous mixture. So we have table sugar, which is called sucrose, fruit salad, neon gas, soda, a chocolate chip cookie, and rust, which the chemical compound is Fe2O3. All right, so if we think about A, table sugar is a molecule called sucrose, and it's made up of carbon, hydrogen, and oxygen. So that would make it a pure substance and also a compound. Fruit salad, you can have whatever you want in your fruit salad, but usually it's a mixture of a bunch of different fruits, and there's going to be distinct phases, so that's going to be classified as a heterogeneous mixture. Neon gas, neon is an element and it happens to occur naturally as a gas, and so that's going to be an element. Soda, that has one phase and it's made up of different compounds, so that's going to be a homogeneous mixture. A chocolate chip cookie, those chocolate chips are not always going to be perfectly distributed throughout the cookie, and so there's going to be phases, and that would represent a heterogeneous mixture. And something like rust, which is iron oxide, that's going to be a compound. It's made up of iron and oxygen in a fixed proportion by mass. We can also describe matter based upon its physical and chemical properties. So the properties or characteristics are used to help identify and distinguish substances from one another. The properties can be broken down into physical things that we can just visually see, or chemical properties that could describe a chemical change. Physical properties should seem familiar to us. A physical property is one that we can observe without changing the identity of the substance. So for example, if we look at this apple, what could we say are some physical properties of it just by looking at it? We could talk about its color. We could say that the apple's red. We could look at its shape. We could say that it is spherical or round. We could talk about how hard it is, its hardness. We could talk about the texture of the apple. The taste, is it sour? Is it sweet? Along with physical properties, we can also describe physical changes that occur. A physical change is a change that is not accompanied by a change in chemical makeup. So we could have a formation or separation of a mixture, or we could have something like a state or phase change occurring. So if we think about the first one, formation or separation of a mixture, imagine having some iron filings and sulfur, which are both elements, mixing them together in a watch glass. You'd form a mixture of the two. But then, if you hold a magnet to that, you'll be able to separate them back into their individual elements because they were not chemically combined and only the iron has a magnetic property to it. This is an example of a physical change. We separated them back into their elements from a mixture. Another type of physical change is known as a state change, also known as phase changes. There are 6 phase changes that you should become familiar with. In each case, we're not changing the identity of this substance, we're just changing what phase of matter it occurs in. When a solid gains energy and goes from a solid to a liquid, this is known as melting. Sometimes it's also called fusion. When a liquid gains energy and goes from a liquid to a gas, this is known as vaporization. Some solids go directly from a solid to a gas in a process known as sublimation. Solid carbon dioxide or dry ice is an example of this. It goes directly from a solid, it sublimes into a gas. Now if we look at the reverse direction, a gas that loses energy and becomes a liquid undergoes a phase change known as condensation. A liquid that loses energy to become a solid undergoes a phase change known as freezing. Sometimes a gas can go directly to a solid and skip that liquid phase in a process known as deposition. Here are some more examples of physical properties, some that we'll talk about in this class, some that we won't. Thermal conductivity, the rate at which a substance transfers heat. We will be learning about heat transfer later on in this class. We just talked about the state, solid, liquid, gases. Density, which we'll learn about later in this chapter, which is mass per unit volume. Solubility of a substance, how easy it is to dissolve into another substance. We'll be learning about solubility in this class. And ductility and malleability are also physical properties. Chemical changes are very different from physical changes. Physical changes didn't change the identity of the substance, whereas chemical changes actually convert the substance into something completely new. This is also called a chemical reaction. The new substance has different properties than it did before, and we can't easily separate it back by physical means like we could with a mixture. Some examples of chemical changes: if you leave some fruit out and the oxygen in the air reacts with it, it becomes oxidized. You can see that by the color change in the apple core. A silver spoon will tarnish over time, and it has different properties than it did when it was just the pure silver. A few more examples of chemical changes include burning toast or cooking an egg. So the key word here would be burning. The key word here would be cooking. When you cook an egg, you change the proteins in it, and you can't easily go back to what it was before. So when you're looking at chemical changes, there's usually some terms that can help you identify that it's a chemical change and not a physical change. Burning, cooking, rusting, tarnishing, all of those terms you should get familiar with to describe chemical changes. A chemical property is something that describes how a substance will undergo a chemical reaction. So for example, the metal zinc will react with acid. Sulfur will burn in the air. Iron, when exposed to oxygen, will rust. All of these describe chemical properties of these substances. The last type of way that we're going to learn to classify matter is through extensive and intensive properties. An extensive property is something that depends directly upon the sample size, or it depends directly upon the amount of matter present. An intensive property is independent of the sample size or independent of the amount of matter present. So notice intensive, independent to help you remember. If we compare sulfur in two different forms, on the left we have sulfur crystals, and on the right we have sulfur powder. So if we look at what are some of the extensive properties of these substances, on the left the crystals have a mass of 39 grams. On the right they have a mass of only 0.84 grams. So it's extensive to say that the mass is an extensive property. Volume is also extensive. The volume is much larger of the crystals on the left than it is on the right. It matters how much is there. Intensive properties are something like the color. No matter how many sulfur crystals we have, the color is still yellow. And because it's sulfur, no matter if it's in a powder form or in a crystal form, or if we have 39 grams or if we have 0.84 grams, it's going to still have the same melting point of 115 degrees Celsius. That's an example of an intensive property. It's independent of the amount of the substance that's present. Let's try an example. Identify each of the following as either a physical or a chemical change. A, sugar caramelizes. B, iron wire glows red when an electric current is passed through it. C, liquid nitrogen boils at negative 196 degrees C. D, tea is made sweet by adding sugar. E, when treated with bleach, some dyed fabrics change color. F, in cold weather, water condenses on the inside surface of a single window pane. G, grape Kool-Aid lightens when water is added. All right, let's go through these. A, sugar caramelizes. So caramelizes is like one of those words like rusting, tarnishing. That's going to represent a chemical change. Iron wire glowing red, that's going to represent a physical change. It's still going to be an iron wire. Liquid nitrogen boils, that's one of our keywords for a physical change. Tea is made sweet by adding sugar. We could take that tea and separate it back into water and sugar, so that's going to be a physical change. Treating with bleach, bleaching is describing a chemical change. Water condensing, condensation, that's one of our physical changes. And grape Kool-Aid lightening up when water is added, those could be separated back, that's a physical change. Lastly, identify each of the following as an extensive or intensive property and explain why. The color of a blue paint chip, the amount of paint needed to paint a room, the weight of the paint left in the can after the room is painted. So A, the color of a blue paint chip, is that extensive or intensive? That would be intensive because it's independent of the amount of matter present. No matter how much you have of that paint, it's going to still be blue. The amount of paint needed to paint a room. However much paint we need to paint a room is going to depend upon how much paint we have present. That's going to be an extensive property. The weight of the paint left in the can after the room is painted. Weight is definitely going to be extensive. That's going to depend upon how much matter is present. So that's an extensive property as well.